All right, so in this new chapter, we are going to work on something called exponential functions. We're going to talk about exponential growth and exponential decay, which is probably familiar to you from some of your science classes. It's a new type of function that we're going to be graphing, and this is going to be a pretty introductory lesson today. We've graphed polynomials before. We've also graphed square root functions in our last section, and we're going to add another thing to our list. We're going to be graphing exponential functions. So first of all, an exponential function is a function, y equals b to the x. So b is going to be some sort of constant. So the base is constant, and then the exponent is the variable. Okay, so that's the important part, is that the base is a constant, and then the exponent is our variable. We've seen the opposite. We've seen like x to the third, where the base is a variable and the exponent is a constant. So this is kind of switching things up a little bit here. All right, now we've got something called an asymptote, which we're going to have on our graphs. And an asymptote is a line that the graph approaches. Okay, so it's a line that our graph will get very, very, very close to as it extends off to the left or off to the right, depending on whether it's exponential growth or decay. All right, so we're going to look at what we call the parent function. Remember, the parent function is the original. Before we move it up, down, left, right, stretch it, compress it, flip it, whatever. So we're looking at the original parent function, okay? So our parent functions are of this form. We say f of x equals b raised to the x. Now, it's very important that b is greater than 1. And that's specifically for exponential growth, that the b has to be greater than 1. All right, so the type of graph, we've got a couple of characteristics here. It's going to be continuous. It's going to be increasing. It's increasing all the time. All right, so this exponential graph, it's kind of a new shape, so we'll see exactly what it looks like. All right, our domain. Our domain is all reals. All right, we're back in the happy, wonderful place of all reals. And then our range is all positive real numbers. So y is greater than 0. All right, asymptote, a line that the graph will approach the x-axis. Okay, so this stuff won't mean a ton until we see the graph, but we're going to write it all down anyways. And then the intercept. We only have one intercept. It's a y-intercept at 0, 1. Okay, so let me show you what the parent graph looks like. All right, so our exponential graph is going to look something like this. Okay, so here, right there is our intercept. That is the point 0, 1. And then when we talk about an asymptote, this is why we call the x-axis an asymptote, because as we go off to the left, it's going to just keep getting closer and closer and closer and closer to the x-axis. And then as we go off to the right, it's going to grow very, very quickly, because this would be b to the first, b to the second, b to the third. So even if we had something like 2, it's going to grow very quickly. 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. That's how we say something grows exponentially. Because if it was a base of 2, every value would double. If it were a base of 3, every value would triple, etc. All right, so this is our very original parent graph. We're going to talk about some different graphs here. All right, so we want to graph 4 to the x, and let's talk about the domain and range. So we want to make a table of values. So let's talk about the positive values first, and then we'll look at some of the negative values. All right, and kind of get into what those negative values will mean. So 0. Remember, whatever these values are, that's what we're plugging in right here for this x. So y would be 4 raised to the 0 power. So hopefully you guys remember this. Anything raised to the 0 power just ends up being 1, which is why we always have this point right here. No matter what your base is, if you plug in a 0, you always get 1. 2 to the 0, 1. 18 to the 0, 1. Doesn't matter what you plug in. Now 4 to the first. 4 to the first, of course, is just 4. Anything raised to the first power, you just get the number back. 4 to the second power is 16. 4 to the third power, I'm hoping we remember this one, is 64. Now let's go backwards. 4 to the negative first. Hopefully you guys remember what negative exponents do. Remember, negative exponents flip to the denominator. So this becomes 1 over 4 to the positive first. and that is just 1 over 4. Here, 4 to the negative second, we again would flip, and we'd have 1 over 4 to the positive second, which is 1 over 16. Okay, so let's graph some of these values. Okay, so I can plug in 0, 1, 2, 3, -1, -2. So 0, let's go up by 4s. Okay, so 4, 8, 12, 16. The 64 is going to be way off the chart, so we're not even going to graph it. So start with the point 0, 1. It'll be right about there. Then the point 1, 4. Then the point 2, 16. And like I said, the 64 will be way off the graph. -1, we're at 1/4. So a very teeny little fraction, and this is an even teenier little fraction, the 1/16. So it just skids along the x-axis, which is why we call that an asymptote, and then this one shoots up very, very quickly. All right, the bigger this number is, the faster it grows. So 4 grows very quickly, 5 would grow even more quickly, 6 would grow even more quickly, etc. All right, we're familiar with transformations by now. We've got horizontal translations, vertical translations, up, down, left, right, and then orientation and shape means, does it get flipped? Is it stretched? Is it compressed? Okay, so let's talk about some of these. So a horizontal translation is based on h. Okay, so h is whatever number you have here. Now remember, as always, x lies. So if h is positive, you're actually moving left. You're moving h units to the left, which is counterintuitive because, of course, x lies. H is negative, you are actually moving to the right. Counterintuitive, x lies. Vertical translation is all based on k. That's the number that's hanging out on the end here. Now, y does not lie. So if k is something that is negative, you're actually moving down just like you think you would. If k is something positive, you're moving up, again, just like you think you would. Now, orientation and shape have to do with a, the constant that is out in front here. If there is a negative out front, then you're going to get flipped upside down. Okay, so if a is less than 0, you get flipped upside down. If a is somewhere between 0 and 1, then the graph is going to get compressed. Which, remember, makes it like shorter and fatter than the original graph. And if a is something bigger than 1, as always, it is going to get stretched, which makes it like taller and thinner than the original one. Okay, so we wrote down some of these changes. Let's take a look at some of these changes. So in example 2, we're going to look at a couple of graphs here. Now, I want us to talk first about what the translations are going to look like, and then we're going to graph it. Okay, so here we have a base of 2. So that's not a. There's nothing out in front of the 2. The base is just 2. Okay, so this has a base of 2, which means each y value gets doubled from the last one. The plus 3 means we are moving 3 units to the left. Remember, x lies. It's counterintuitive. And the minus 5 means we are moving 5 units down. Okay, so here's what I want us to look at. In my original parent graph, every single one of these graphs has the point 0, 1. And then it kind of takes on a similar shape from there. So the point 0, 1 is our original point. Well, instead of starting at 0, 1, we're going to go 3 units left and 5 units down. So instead, I'm going to start at -3. That's my 3 units left. And then from 1, I'm going to go 5 units down. So I'm going to go down to -4. All right, and then I'm going to graph what a 2 to the x graph would look like. Okay, so I am going to go 3 units to the left and then 5 units down, which lands me right here. Okay, and then what happens, the x-axis used to be my asymptote. Now my asymptote is actually going to be 5 units down. All right, so I'm just going to throw in a little dotted line. All right, and then it's going to look like this. Drags along that, goes to this point, and then it shoots up pretty quickly. All right, so it's going to look something like that. So my domain is always all reals. My range, I moved 5 units down. So instead of being anything greater than or equal to 0, it's now, I'm sorry, not greater than or equal to, just greater than. It's now going to be anything greater than -5 because I moved 5 units down according to this number right here. Okay? Next one. My base is 6. That's that number right there. Now, x, I don't move left or right at all. Okay, so I'm not going any units left or right because I just have an x. This -3 tells me I'm going 3 units down. And this number out front tells me I am compressed times 0.1, which is a tenth. So that means it's going to be very short and fat compared to an original. All right, so let's see what that's going to look like. So my original starting point is 0, 1. So I am now moving no units left and right, so I'm still starting at 0, and I'm moving 3 units down. So from 1, I move 3 units down to a -2. And then my asymptote moves down 3 units. All right, so that's still going to be my asymptote. Okay, so now just a very brief sketch. The base is 6, but it's getting very compressed. So it's going to be very, very short and fat. So it's going to look something like this. So it's not going to grow very quickly at all compared to some of the other ones, and that's because of this compression. All right, let's take a look at exponential decay. These ones grow as you move from left to right. That's why we call them exponential growth. These ones are going to decay as you move from left to right, which means they're going to get very small very quickly compared with the original exponential growth. So that's our second type of exponential function is exponential decay. The way we tell the difference, they still look like this, except in this case, our base is going to be somewhere between 0 and 1. So we could have a base of like 1/2 or a base of 1/3 or something like that. All right, this type of graph, it's still a nice continuous, smooth function, but these ones are going to be decreasing instead of increasing. That's the big difference between exponential growth and exponential decay. Our domain is still all reals, and our original range is still positive real numbers. Okay, these other things are still the same too. Our asymptote is still the x-axis on the original parent graph without transformations, and the intercept is still 0, 1. Okay, and we'll see exactly why once we look at one of these graphs. So exponential decay is going to look like this. It still has this point right here because it does not matter what the base is. If you raise it to the 0 power, you're still going to get 1. Decay looks like this. Okay, so notice we still have this value as an intercept. We still have the x-axis as an asymptote. It's going to get really, really close to that line right here. So we still have that point. And then we've got a whole bunch of different points depending on what the base is. Okay, so I'm not going to rewrite all of our transformations again. We still can move left, right, up, down. We can get flipped. We can get compressed. So I'm not going to write all that again. We're just going to look at a couple of examples here. Okay, so the first one, we are going to graph this very carefully, and we are going to look at an actual table, and then part B, we're just going to graph using transformations. Okay, so we're going to set up an XY table. Again, we are going to start with the positive values because they're easier to deal with, and then we're going to look at a couple of the negative values. All right, so if I plug in 0, remember 1/5 raised to the 0 power gives me 1. Does not matter what the base is. If you raise to the 0 power, you're going to get 1. Now raise this to the first power. Take 1/5 and raise it to the first power. Well, I know I'm going to get 1/5 because anything raised to the first power just gives that answer back. 1/5 to the second power. That means we square the 1 and we get 1. And we square the 5 and we get 25. Okay, now the negative exponents. The negative exponents are a little weird. If I take 1/5 and I raise it to the negative first power, remember how negative exponents flip? So what I actually do, see how my fraction is 1/5? The negative exponent means I flip to 5/1, and I change my exponent to the positive one. So 5 to the first, of course, is just 5. And then if I have 1/5 and I raise it to the negative second power, Remember, the negative exponent makes my fraction flip to 5, or 5 over 1, and the exponent becomes positive. So 5 squared, again, of course, is 25. So now let's plot these points. So I have 1, 2, -1, -2. Let's go up by 5s. 5, 10, 15, 20, and 25. So my points, I have the point 0, 1, right about there. I have the point 1, 1/5, so we're just going to get closer and closer to the x-axis there. Graphing 1/25, not going to be incredibly accurate. So now -1. -1, we're up here at 5. And -2, we're all the way up here at 25. Okay, so exponential decay looks like this. It starts off high, and it goes very, very low, and then it just sort of drags along the x-axis like this. All right? So that graph is going to look something like that with a base of 1/5. Okay, let's look at one last example right here. So let's talk about all of these pieces. This -4 out front. The negative means it's going to get flipped. The 4 means it's going to be stretched out times a factor of 4. So it's a vertical stretch. The base is 1/2. X minus 1, remember x lies. So the -1 means we're moving 1 unit to the right. Okay, and then the +2 out here means we are moving 2 units up. So let's start with this. My starting point again is normally 0, 1, but I'm moving 1 unit to the right from 0 to 1, and I'm moving 2 units up, so from 1 up to 3. Okay, so let's start with this. So I'm starting at the point 1, 3. I've got that much going. And now this part gets a little bit weird. So normally my my axis of my x-axis was going to be the asymptote, but everything is getting moved around quite a bit. Okay, so it's getting stretched times 4. It's getting flipped over upside down. So moving here, I'm still flipping my graph upside down. So let me show you what the original would look like. The original would look something like this. So I'm just going to do this in pink so you can compare. All right, the original would look something like this. It's getting stretched out a little bit, looks something like that. All right, but I'm flipping my graph upside down. So it's actually going to look something like this. Okay, so just flipping that graph upside down. So the black one is the real graph. Okay, so just kind of comparing the transformation, the left, right, up, down, stretch, flip, the stuff that we already know, combining that with a brand new topic of exponential equations. All right?